Hello everyone, welcome to another video in the Transformer series. Today we're going to be looking at attention module. Specifically, we're going to be looking at the scale dot product attention. We're going to start off by looking at what is attention module and then understand how it works at the inference stage. So let's start. Now let me start off by giving a sentence. Let's say I wrote the sentence, I am going out. Well, for any sentence, it's really important for us to understand the context of a particular word in the whole sentence. That's when we can make a meaning out of it. Now, what I really mean is that if I just give you the word going, you cannot really make a sense of it. If I give you the whole sentence, you understand the purpose of this word in the whole sentence. So this is the idea behind the attention module, that like a representation of a word is not only by itself, but the surroundings also add a lot of value to the representation and helps us understand more about the sentence. Or in another way, we can look at it as helps us gain more sense or meaning out of the sentence. So let's start. Now let me take an encoder block here. So let's say this is an encoder block. Usually, like in the transformer, let's say this is an encoder block. Usually there's like an attention module here, and there's a feed for a neural network here. And I'll do a quick recap. Like let's say any word, if you're considering generating an embedding for the word I, the goal of this attention module is to give a good representation. Now in this video, whatever we look at, we'll be looking at what's happening inside this block. So the goal is to give an input, a vector of whatever size, and to get an output vector. But the difference between these two vectors is that this vector represents the word itself, but this vector represents the word and its contextual information, the surroundings. So that's the aim of the attention module and the key idea behind the attention module. So let's see how we go from here to here. And a quick recap of how this is formed is that given a word, we usually have like let's say the word I, we usually have like an initial representation, and then we grab the positional embedding, we add the positional embedding, and then we have the final embedding. Now this representation is a representation that's this and this are equal. So let's look at how we go all the way from here to here. Now I'll consider a vector of size 5 and 2. Usually that's the size of the original transformer paper that they use. So let's start with the sentence. Okay, let's take a sentence. I am good. Now let's say I have this sentence and I want to like generate a representation through the attention module for this. So initially I'll have the vector. Sorry for the bad drawing again, I'm getting used to this pencil. So let's say I have a vector. These are size 5 and 2. This is like a combination of the initial representation plus the positional embeddings. Now this would be the final representation. Now this is what we're talking as this. This is the input. So let's just take like one word, understand how things work, and then the same concept applies to the rest of the words. So if I do take the word I, and let's say like this is an embedding 5 and 2, I'm drawing the same one here. So what really happens in the start is that if you look at the attention formula, it's something like this: Q K transpose by root of dimensions into the value. Now we'll see how this formula applies to this vector. So what really happens initially is that by this point you should be aware of the artificial neural networks. So we'll consider 3 neural networks. Okay, like let me call this an ANN, but with no activation functions. It's just going to be a linear projection. So we consider 3 neural networks. So I mean, like, simply understand that like we give the input into the neural network, we're gonna get an output. We're gonna pass the input size and the output size as the parameters. So let's just say I'll pass this 5 and 2 size vector into these three, and then I'll get like 3 vectors each, and the output size is gonna be 5 1 2 2 for, so this is gonna be, I'm gonna explain what is QKV, but let me just finish writing here. Yeah, so we take the vector, we pass it into 3 artificial neural networks without an activation function. It's going to be a plain linear transformation, and then we're going to get an output vector. So these are Q, K, and V values. That's the query, key, and value. Value is self-explanatory. It's the representation of the word itself. Keys are attributes, and then queries are like the questions we're going to ask about the sentence. You can somewhat think of it like that when you're going for intuition. So, and then we basically apply this formula on these. So now that we projected this into this, these 3 forms, like these 3 vectors, we're going to do that for all the 3 words. Now the 3 words we have are I am good. So let's just see in the end what really happens. Like, let's say we have the word I am good. Like, let me write it properly. And we have Q, K, and V, and we have like this boxes. These boxes are nothing but the query, key, and value vectors. I'm sorry for the drawing. I'm just gonna put it here. Yeah. So now we have query, key, and value vectors for each of the words. Okay. So the first step is that we take one query value. Let's take the word I. We take this value, and then we multiply it with this. Multiply as it's a dot product, so we're going to end up with like one number. So let's just say I multiplied these 3 with this 3, and like let's say I end up for the word I end up with these 3 values, 5, 2, and 3. Okay, now a dot product would give me these results. Let's assume that it gives me these results, and what I will be doing with these results, so this when I do the dot product, that's where we are talking about Q into K transpose, this part, and then what we do is usually divide it by the root of the dimensions. Since we know that each vector is of size 5 and 2, that's the dimension of the vector. So this point is usually called scaling. We do that so that the values don't blow up. I'll be giving more intuition as to why we do that, and like how the activation function really takes a hit if you don't scale it. So we're going to be scaling it with the dimension that's like root of 5 and 2, and like we're going to be dividing every value. So we get like, I'm not going to calculate that, but let's just say we get like 3 values, x, y, z, and this goes to this. And then now what I'm going to do with x, y, z is to pass it through a softmax. Now basically there are a lot of resources out there to understand how softmax works, but like basically it's gonna give us a probability distribution. So it's gonna give us 3 numbers. Let's take them as A, B, and C, and these 3 numbers are gonna add up to 1 because it's a probability distribution. So out of 100% we have like values of how much each of these vectors make up. Now let's assume these values are somewhat like 0.6, 0.1, and 0.3, because these have to add up to 1. That's the property when you pass it into a softmax function, and we have 0.6, 0.1, and 0.3 after passing it through the softmax function. So basically we've completed the everything in this formula except multiplying it with v. Like, sorry, it's a dot product. So I'm so sorry, it's so messy. So these are the value vectors, right, that we have, and we talked about it, that value vectors are something that represent the word itself. So these are the words these are something that's representing the word. So what we do is that now that we calculated the attention for the word I, we're going to take the I value vector. This is the I value vector of size 5 and 2 again, and we're going to multiply it with this. Sorry, we're going to take the I value vector and multiply it with 0.6. We're going to take the am value vector and multiply it with 0.1, and we're going to take the good value vector and multiply it with 0.3. So sorry, I know it's gonna, I'll just like take it down somewhere else. So we're gonna take 3 value vectors and multiply it with 0.6. That looks like a 1. Multiply it with 0.1 and multiply it with 0.3. Remember how like these 3 add up to 1, and then what we're doing is we're taking, so initially the word I, its representation only consisted of the information for I. So now after the attention module, what we came to know is that for the word I, in order to form a representation for that particular word, what we really need is 60% of the value of I plus 10% of the value of am and 30% of the value of good. We're going to concatenate these, and the final vector representation is going to be a vector of 5 and 2. But this representation is not just for the word I. It consists of 60% of the I value, 10% of am value, and 30% of the good value. That means good is adding 30% value to the word I, am is adding 10% value to the word I. Now we know that the I's representation is very rich when compared to the previous representation, as we have the context information of how much value is coming in from the surroundings. Similarly, I know this is confusing, you have to go through it multiple times to understand this, but similarly for the word am, we form a representation that's of size 5 and 2, and similarly for the word good, we form a representation that's of size 5 and 2. Now this way, like we could get, let's say for am, we could have values like 0.1, 0.7, 0.2. So we're going to multiply 0.1 into the value vector of I, and 0.7 into the value vector of am, and 0.2 into the value vector of good. So similarly, that way we form 3 representations, but these 3 representations consist of paths from the other words representation too. That's what the attention mechanism is doing. It's really adding the contextual information, but also it's telling us how much of contextual information is required. As to like when we look at I, that like 60% of I is required, and 30% of good is required, and 10% of am is required to form a vector representation for I. So this is what the attention mechanism does, and I'm not going to be talking about multi-headed attention right now. That's going to confuse. This is the drawing is actually itself in here. It's going to make it a lot more confusing. So this is it. I'm going to be posting another video talking about multi-headed attention, and also there's another type of attention called master attention. It's a variation of this, but very interesting to explore, and that's used in the decoder, and it makes sense. So this is what we really anticipate out of it. So initially, like with the encoder block and an attention module in here, the output we're getting here, the intermediate representation, that is this. So we pass an input and then we're getting a representation here. That's what we're looking at here. So this video covers how the attention module in here works, but I haven't covered the multi-headed attention yet, so I'll be filming a video on that too. Thank you for tuning in. I hope you enjoyed the video. See you in the next one.